So we are still talking about this cascode, CS cascode with inductive generation, right? I'm going to repeat some of the material before, just as a part of review for the exam. The main thing is that this CS cascode, common source cascode amplifier with inductive generation, is like in this circuit, right? Put an inductive degenerative impedance at the source. Of course, you should know what is source, what is drain. You should be able to draw the small signal for a transistor. Even you don't have much background, I'm sorry, you need to do that. Put in your cheat sheet if you are not sure if you can draw the small signal for NMOS and PMOS. And at that time, we only look at the bottom part. And we go through a lot of KCL, KVL, but you need to understand, but don't worry, I'm not that crazy. I want you to do this type of math in the exam, right? It doesn't make sense. I'm not trying to test your algebra skill, right? But the main thing is that you should know KCL, KVL, and what we said last time, after we solve this circuit, we realized that the input impedance, again, what is the input impedance, right? You need to know the definition, input voltage divided by the input current, right? Eventually, I came out with Z in equal to Vx divided by Ix equals to this term. It has imaginary part, it has a real part. And we say that if I set this real part to 50 ohm, isn't that I will be able to match the input impedance, right? Then that's done. And this is just a function, right? A functional form of Z in. But if you look at it carefully, wow, this is just the impedance of a capacitor, impedance of an inductor, and an impedance of a resistor. So I can draw this equivalent circuit. I'm not saying that this circuit is composed of this circuit. I'm not saying these two circuits are the same from every aspect. I'm just saying that looking into the input, the impedance I saw in this circuit is exactly the same as I look into this model. Do you agree? Yeah? So that is one thing. And we say that if you do some calculation, you find that you need a very small inductor L1, because now you're relying on L1, GM L1 divided by CGS1 to decide the impedance, right? And we also, what is GM divided by CGS1? Transit frequency, right? I know he is expert in this area, he can say it right away, but I feel that anyone who is going to do an interview with RF or whatever company, you should know this term, right? That is the basic. Just like if you want to be a device engineer, you should be able to say what is VTH, what is threshold voltage, right? Okay, then we try to do some circuit transformation, right? In order to, this is just for us to use later. These are some good equation, but it will be good to understand that, well, if I have an inductor in series with this one, right, it's equivalent to have, not inductor, sorry, I have a reactive component, JX1, can be inductor, can be capacitor. If I put it in parallel, it will be exactly the same if I change my RP to this value, x1 squared divided by Rs, or x1 squared divided by Rp. Then they will be equivalent if you relate these two together. Right? And the reason we study this is just because we want to further understand what is the effect of the pad. For example, in this structure, we have the input antenna, right? Maybe bond wire to wire bond to the pad, and then now you go into this input of this low noise amplifier. So I have this extra C pad, and then went through a lot of math. It's just a procedure, right? You try to follow this procedure, you will get the answer. So this is just a practice. And after all, then we say that, hey, with this pad, right, pad capacitance, if it's similar to CGS, you actually reduce the effective real part of this impedance by 4 times, approximately by 4 times. Then earlier we say that we need to have a pretty small L1 because we want to have a GM-L1 divided by CGS equal to 50 ohm. But because of the effect of the pad is further reduced by 4 times, so now I can have L1 to be 4 times larger, so that effectively I have 50 ohm. Okay, these are just some skill, right? And then with that, after you are done with this, then we're going to add an inductor, add an inductor to match, to cancel the imaginary part. Then the whole thing will become pure and real, right? So again, what is the strategy in all the circuit design? We come up with some idea using inductor or capacitor to form a complex input impedance, right? You have a C in, which might be equal to real part plus JX. However complicated it is, we then adjust the element to make this 150 ohm. Of course, when you adjust this, X will also change, but usually it won't be 0. Then later, we are going to add another component. For example, if X is positive, we add a negative JX to it to cancel it. If X is negative, we add a positive JX to it. Under what situation will you get a positive X impedance? It means J times a positive number. It's inductive. Very good, right? So you will add a capacitor to cancel it. If it's negative, means your input impedance is capacitive, you add an inductor to cancel it. Okay? Yeah. So this is the idea, right? So that's why I said, although we are still learning something new, you might need to do this in your finals, in your exam, right? So these are just the basic skill. Okay, then our main goal, no noise amplifier, of course, is to calculate the noise. But in order to calculate the noise, I also need to calculate the gain, right? Why? I asked you many times why I'm interested in the gain. Because the gain is used to calculate what? Noise figure. And definitely those equations you need to be very familiar with, right? You can put in your cheat sheet, but make sure you understand what you're writing, okay? So you can put the right term. Now, as I said, you should know how to draw the small signal model, right? So now we draw this one. This is the full circuit, or DC, right? So we draw small signal, G, VGS, I add everything. CGS, CGD, RO, which is the channel length modulation. If I don't ask you to ignore, don't ignore it, okay? And then L1. And then just be very careful, add back everything I need. Now here I don't have the inductor LG, but in reality I have, right? Just because I copied the figure, that's not that complete, because we do need this LG to do the cancellation, so I add LG. And of course you should know how to draw the noise, right? For the transistor, there are 3 types of noise in a transistor. What are they? Thermal, flicker, and flicker is we don't talk about short. We have not discussed short. But what I'm more to say is that one is the thermal noise from source to drain, another is flicker, another is the thermal noise due to the gate resistance. But usually for a well-designed transistor, that should be small, right? So we usually ignore it, and it has been almost in every problem I say we also ignore flicker noise. Actually, it is wrong to ignore them, but I just want to make things simple, right? So I have 3 noise. So this is the major one we have been playing with. It's 4kT gamma GM. Again, when you talk about noise, we talk about power spectral density, right? So it is square bar. So the unit is ampere square in this case, right? So what did we do last time is that, okay, I say we may have V in, we may have noise, we put them together. This is just like one stone, 2 birds. You can actually do it 2 times. I just follow the approach from the textbook. They try to derive everything at the same time. So a lot of complicated math we won't repeat. Go through all this complicated math, right? Then eventually we have this equation. V in as a function with I out, and also as a function of noise. But now it's the value of the noise, right? We are a little bit nervous that, oh, what is the direction of this noise? In this equation, it might matter, but our goal is not to have an exact form. Our goal is that we want to relate V into I in and I and in later, and then we're going to take the square because we only care about the power, right? So don't worry, if you put plus, you will get the same results, right? So that's why we have been asked, or you always ask me, I ask myself, where should I put the direction? It doesn't matter because it's a noise. Over the time, you go up and go down, right? So you don't have a direction. It's small signal, it's AC, right? So then with this, one more important thing is when we simplify the circuit, we need to remind ourselves we operate at the frequency we want to operate at. So at that frequency, what do? We have impedance matching, right? So in that case, you will see that there will be resonance. So this whole term is gone, right? But anyway, so what we are doing here is this is the V in as a function of I out as a function of I in. And then we do it one by one. Now, when there's no noise, then because there's small signal, we talk about this superposition of noise power, right? Or just the power. Then IN1 equals 0. This is gone. Then I can get the gain easily. Okay. Eventually, the gain of this circuit is omega t divided by 2RS omega 0. Again, what is omega t? We just discussed. Transit frequency. And what is the formula for transit frequency? Anyone else? GM divided by CGS. Right? We discussed many times, right? Again, this is like, if you want to show people you're good, then you should really memorize it. Although we don't encourage memorization nowadays, but you're really good at something, you will memorize. What is omega naught? Whenever you see naught, is the resonant frequency, which means it's the frequency, the operating frequency, right? Okay, so this gain is pretty large. It's very encouraging because transit frequency usually is much larger than the operating frequency, right? So the gain is very large. That is the hint why this one has a very low noise figure. Okay, so this is the gain. So again, as I said, why is it so complicated? Because we try to have one stone, two birds. We have the noise and the input at the same time. We could have just removed this noise and just solve the gain. You will get the same result. Now then we continue with this equation, and now let's look at how the noise is related to V in or I in, right? So let's just look at the for noise. Yeah. Mm-hmm. Noise current of the input reference noise, or no, I mean yes, what not we short the input. Yes, it means V in equal to 0. Yeah, well we want to see how much noise is at the output. Very good. Yeah, so I did not mention this. Here is trying to say if I certain input, how much output current I have. And the second step is if I have this noise, how much output current I have. And this output current is going to be caused by a noise. And that's why your output has noise, right? So now we're going to make V in equals 0, right? So we're going to make V in equals 0. So consider noise only. In this case, V in equal to 0, right? So with V in equal to 0, I just need to play with the equation. I have I out L1S plus I out. Actually, this one got cancelled already. Yeah, so this one I should actually make it simplified because I already say that this term got cancelled, right? Before, during resonance. So we only have this equation. Okay, this term got cancelled because of the resonance, right? We said last time. So it is better I just cross this out so you won't get confused, right? Resonance at omega 0, right? So you only have these few terms. Then I have 0 equals to IOL1S plus IO times RSCGS1S divided by GM equals to, not equal yet, let me continue to minus IN1 times the same term. Is this okay? Right, what I'm doing is just 0, right? We need a 0. And then this term copy here, and then I out times this whole term, and then minus I in times this whole term. Okay? And my goal is to find out what is I out divided by I in, because my goal is that you have this, not I in. What should that be? IN1, right? I want to know what is the output current due to the noise, and that is the noise at the output, right? And what I also only interested is the magnitude, because later I'm interested in the power, right? I don't need to know the direction. So you just arrange the terms, right? I in, maybe go to other direction, and then go down, right? So you have RSCGS1S divided by GM, the whole thing divided by L1S plus RSCGS1, sorry for my writing, CGS1S divided by GM. Is that okay? Right? Because you just multiply IN1 times this one, right? And then I out times this one, right? Then it's just I out times the whole thing, and then IN1 times this whole thing, right? So with this, just do some simplification. Actually, RS is going to get cancelled and times GM. Then I get RSCGS1, right? GM, S is got cancelled, right? S. Right? And then you multiply by GM, you get RSCGS1 plus L1GM. Okay? But we know that, remember how we do this RS? If you remember, the RS, which is the real part of the input, we match it already, equals to what? L1 times GM divided by CGS1. This one. We say the R1 equal to GM times L1 divided by CGS1, right? When you match the impedance. And this one is just RS, right? We call it R1 here, but that is just RS. Because you match the source impedance, RS, 50 ohm, right? Any questions? Yeah. No, resonance is talking about this one equal to 0. And we proved that earlier, right? At resonance, you have this circuit. It is 1 over L plus this one. Yeah, so then you get this one. So you need to go through the math a little bit. Is that okay? Right? So with this, then I'm going to substitute the RSCGS. So this, maybe I better use another color, right? This one, I'm going to substitute to here. Then what do I get? RSCGS1 See this? Rs times CGS1 is just equal to L1GM, right? How about the bottom? L1GM plus L1GM. What is this? Just equal to 1/2. So what is the noise at the output then? Due to this noise source. Of course, it's equal to IN1 square times just look at this one. I out divided by I noise equal to 1/2. Then what is I out squared? Just the whole thing divided by 4. Okay? Which is equal to what? What is the IN1 square? 4KT gamma GM. Very good. Which is equal to KT gamma GM. Okay? So this is the output current noise. Okay, so we finished this step. Any questions? Right, so we got the gain at the output. I mean, the whole circuit, we got the gain at the output. But now let me ask you one more time. Ask you one more time. Very good. He said this is just a common source, not a common source with Cascode. But one more important condition. We assume the output is grounded. Right? I ground the output to get all this thing. Do you still remember why I ground it, although it's written here? Do you still remember why I ground it? Because we know that we are going to use this equation in the common source with Cascode. And the impedance you look into the Cascode transistor is very small. It's 1/GM. That's why I try to approximate it as grounded. Okay, so let's take a look later, right? So here is summary, right? So we just say that the gain equals to capital GM, right? Why GM? Because it's I out divided by VE, right? Equals to omega T divided by 2 omega 0 Rs, right? Let's check. This is what we got earlier. Omega T divided by 2 Rs omega 0. We also say that the noise, right? Output noise. Output current noise due to the transistor is what? Instead of 4KT, it is KT gamma GM. Okay? So what is the noise figure? What is the noise figure for this part? Remember, I'm talking about, this is very important. I'm still talking about with grounded output.
Are you going to refer these noise back to the input?
Yes.
And then put the because they're always.
Yeah, I'm doing that. Let's do it step by step. So what I'm doing now, again, is the noise figure for common source only, no Cascode, right? With L degeneration and grounded output. So what I'm doing now is just this circuit. I'm doing this circuit, right? I'm finding the gain of this circuit and the noise of this circuit. And what is the noise figure? By definition, that's why you need to know, right? It's 1 plus you can do the input refer noise first, right? Which is KT gamma GM. Why don't I do 2 steps as a hint for your exam, right? I don't need to do these 2 steps, right? So what is the input refer noise? equals to, the output divided by capital GM square, right? Input reference noise, right? If you don't understand, go back to study. Right? That's one thing, right? This is one way to do it, but actually it's the same. The results will be the same. So this is KT gamma GM divided by this whole thing, omega T divided by 2 omega RS square. This gives me the input reference noise. If I want to find the noise figure as a function of the input reference noise, I'm going to do, how about I just call this VRF, right? It's not consistent with my previous, I don't know if it's consistent. Divided by what? You need to further reference to the 4kTRS, right? That is how you get the noise figure. Well, of course, we also discussed that we did not have a step in between. We just state that, well, it is just the total noise at the output divided by the gain divided by the reference, right? It's still the same, right? That's what I had before, but as a hint for your exam, right? Second time I say it. So now I'm going to do this, then it's KT gamma GM. I just copy everything. Omega T square, I'm going to put this to the top. 4 omega naught square R square. I hope you see what I'm doing. What I'm doing is, I try to copy this input reference noise to here, right? So it is 4 KT gamma GM, and I keep omega T square at the bottom. I bring 4 omega square R square to the top. Do you see that? Again, 4R ref square bar is 4 KT gamma GM, 4 KT gamma GM, divided by omega T square, further divided by this term, but now I put in denominator, numerator, it becomes 4 omega naught square R square. Make sense? And then I need to remember to put 4 KT RS. So what is this? Right, let's do some cancellation. KT gone, 4 gone, RS gone by 1, right? So this is equals to gamma GM omega naught square RS divided by omega T square. Let me further arrange it to make it clear. 1 plus GM RS gamma omega naught divided by omega T whole thing square. Okay? Right? I just put this one out, right? Omega naught divided by omega T whole thing square. What did we just say? What is the ratio between omega naught and omega T? What is omega naught again? Operating frequency. Maybe you're doing superconducting qubit. Well, I'm just reading it 7 gigahertz. But what is the transist frequency of the state of the art transistor? Yeah, more than 100 gigahertz, right? So maybe 50 times. What's 50 times square? 1 over 50 times square, right? It's talking about 0.0001. What is 0.001 times this probably small number RS times GM? So what is the noise figure of this whole thing? Almost equal to 1. Right? This is the first time we see something way lower than 3 dB. But of course, we're only talking about the first stage, right? But at least this looks promising, right? So now, then we continue. We have this noise figure is about 1, and then we look up, right? We know that this can be treated as another transistor, another stage, right? You can say that I convert voltage to current, and now it's the current as the input to this. What type of amplifier is this? If just looking at this one, input is going in, common gate, right? Because the gate is at constant voltage, right? And then this is the output. Yeah. Yeah, we will analyze the whole thing, but step by step. Of course, you can do it in one step, right? As a whole circuit, but that is time consuming. I mean, that is complicated. So we want to break it into different parts, make it easier. I'm going to do that, right? So we already only done the first part. So first of all, now, as he said, you want to analyze the noise figure of the whole thing. The first thing you need to ask again is the gain of the whole circuit. What is the gain of this whole circuit? So this is this one we discussed earlier, but you probably forgot, right? I'm going to use what we learned before is the capital GM of this circuit times the output impedance of this circuit. We did learn this before. Did I mention this? We mentioned this is E124. I think I did that, right? In Cascode. I think so. But anyway, I won't test this. Another thing, another good hint. I won't test this equation in the exam, so don't worry. For any complicated circuit, I think I mentioned that before. However complicated it is, 1 trillion transistor, you just need to find the effective GM. What is GM again? How do you measure transconductance? GM equals to, say again, I out divided by V in with V out grounded. Right? That's how you find the GM. So if you want to find the whole GM, this transistor solve small signal model, you ground this part and then just solve the small signal model. How do you find the R out of a circuit? V out divided by I out with in equals 0. He know this because he's the TA of 124. but also he learned it before, right? But no, he's expert in this area. If you don't know, not a problem. But at least you should know that it has a definition. Look at cheat sheet or Wikipedia, whatever, right? So that's why I say the whole circuit is just GM times R out. Now, so let's do it one by one. What is GM of this circuit? Is the GM of the Cascode circuit common source with Cascode, right? Is equals to just equals to GM itself. And I forgot this is negative capital GM out. Okay, it's just equal and it is 1 GM1. Okay, and the RL is what? If I ignore channel length modulation, it is just looking into here. Since no channel length modulation, looking down, you have infinite impedance. You're looking from here, looking down, right? Here is infinite. So what is the input impedance when you look up? You only have this one parallel with this. What's the input impedance? He said R1. Do you agree? Looking up, yeah. What is the impedance that you see? Huh? Looking up, what's that? He said R1. Okay, then he said LD and C1, right? Both of you are correct. Under what situation is R1? It's resonant. And you're also right because it's for every frequency. Okay, so remember this, right? Once you are at resonance, things become so easy. So yes, R1, right? So then with this, we know the GM already. No, not GM2, but I think I say something wrong. It's not the GM of this lower transistor because
I thought we were.
no, I'm looking the whole circuit, not second stage. So I was wrong at the beginning. I told you that I'm trying to break it because I forgot I wrote in cheat sheet. But now we just look at the whole thing. Okay, but
So you didn't finish the previous one. The previous one you left out.
so the previous one is this. I'm talking about this current I So here I'm saying something wrong. I'm not going to correct it, okay? The previous stage is this I, let's say call it I dash. We have the GM equal to I dash divided by V in. This is the previous stage. Where's that? Here, right? We were talking about, we ground this part, right? So we're talking about this I out divided by V in, right? This is the GM, the gain, the GM, right? So here we should use actually I dash divided by V in. So I said something wrong. And what I was saying was, again, without inductor, just at DC. So this is I dash, right? So what did I say wrong? It is this part. This GM is not equal to the GM of this transistor. Sorry for that. This is a mistake because we're looking at high frequency, right? So we have all this thing here. Okay, so what is that? That was just we proved earlier, which is omega t divided by 2 omega naught R S. This one. Okay, this is the GM, which is the gain, right? Output current divided by Vm. So I'm wrong about this. Now, but then whatever current goes in will go to the drain also. Okay, the gain, the current gain from the source to the drain is 1. Right? Just think about that. If you ignore the channel length modulation, you increase the source current by delta I. All this delta I will go to the drain, right? So the GM should be, let me be more specific, right? If I call this I out, GM should be equals to I out divided by V in, which is equal to I dash divided by V in times I out divided by I dash. Do you see that? Because I dash got cancelled, right? The GM of this whole circuit is I out divided by V in. Makes sense? I confuse you, but let me correct it. I out divided by V in. Right? You agree? GM? And of course, I can break into two parts if I know what is I dash here, right? Which is I dash divided by V in times I out divided by I dash. Right? So let me make this very clear here. Yes. So this is I dash, and this I dash equal divided by V in is equal to the GM dash from previous slide. Okay? But I dash divided by V in, I just told you, it is equal to what? It is equal to omega t divided by 2 omega naught Rs. Right? We proved that. And then this is about equal to 1 I naught divided by I dash. Okay? So with this, then we say that the total gain, the gain is equal to negative omega t divided by 2 omega naught Rs times R1. This is the total gain of this circuit. This is a voltage gain. Okay? So I confuse you, but let's just step back. All I'm doing is just that I want to find the total gain of this circuit. But I already know what is the GM from here to here. And I also can easily know that this is about 1 from here to here, current gain. Right? So I know what is the GM from here to here, from the input to output. And then negative GM times R out will give me the gain of this circuit. Okay? Yeah, this is intermediate node already. You cannot, because then this has a low input impedance, right? You cannot decouple them. When your loading has low input impedance, you cannot just chop them, right? If you have very high input impedance, you can chop them to equation and do multiplication. And that's why we use current, because if your input impedance is 0, again, I can chop them into 2 parts. No. If you get, okay, but then you are not really chopping them, right? You already see 1/GM, yeah. But then you need to put this 1/GM into.
I guess the reason
But the point is you don't have much swing. That is the point. If this is ideal, you don't have swing, you only have current swing, right? Because the loading is so small. If this approximation is correct, you don't have swing. No, you can have current amplification. Yeah, you do have a little bit. Yeah, but just, of course, you always have, but the point is you also can look from the current point of view, right? Yeah. Let's don't, no need to, yeah, let's go ahead. It's the same, but not as handy as this one, right? Because the loading is 0. That's why we do that, right? If you do 1/GM, the equation is very complicated. Once you add 1/GM to here, then you need to solve everything. You can do that, but it's not as easy as this one. Okay, so then how about the noise figure? The noise figure is that now I have one more source of noise, which is due to the R1. Okay, so the noise figure due to R1 is equal to 4kTR1. The R1 has a noise, right? 4kTR1. And where does they go? Because the input impedance is 0, right? So I mean, 4kTR1 is here, so you feel at the output already. This is the voltage noise. You feel at the output already, right? You don't need to do any transformation. But then I need to do it by the gain square and then refer to 4kTRS, right? And what is the gain? We just found the gain from the last line. What is that? It's this one, right? So it is omega 1 R1 divided by 2 omega log Rs, the whole thing square, right? Times 4kTRS. So this is the noise figure contributed by R1. So let's remove that. R1 Rs will get removed by this square also, right? We have a 1 less R1 divided by Rs. So this is equals to Rs divided by R1, the whole thing, and then maybe 2 omega 0 divided omega 1 square. 4, sorry, should be 4. Yeah, say again. No, I'm just saying that the noise figure due to R1, further contribution by R1. I have not give you the noise figure is talking about the whole circuit, right? Now it's saying that the noise figure contributed by R1. I'm just giving you what, because we are doing this in superposition, right? Just now we already done M1, right? M1 will give me this noise figure. M1 give me this. Because without M1, without R1, you always have 1. The noise figure needs to be 1. Right? So this is not due to any of other parts. Understand? So this part is due to M1. And now I'm calculating the part due to R1. Okay? And then with this, the total noise figure is of course, is what we have 1 plus Gm Rs gamma omega 0 divided, this is T, omega T square. This is due to M1 plus 4Rs divided by R1 omega 0 divided omega T square. This is due to R1. No. When I say I tell you the part of the noise figure due to R1. Noise figure has 3 parts. Then I'm trying to say.
That's fine. I guess I'm trying to connect it with the basic equation.
What basic equation?
1 plus b squared.
But that is the total noise figure.
That's what you're
No, then you have 2I, 1. You see, if you want to do that thing, the total noise is equal to this one and this one. The total noise due to your amplifier is this part and this part.
exactly, yes. That's what
So you cannot have 2, 1 at the same time.
yes.
And then this component due to the source.
Yeah,
Yeah,
this
that's here. Yeah. This is AV squared. What do you mean I divide already? That's how you find the noise figure. Right? Okay, so then we're done with this one. I want to do one more thing.